Causality is the most fundamental law in physics. Not a law in the sense of a rule that was discovered and might have been otherwise, a law in the sense of a logical necessity, a prerequisite for physics to make sense at all. Cause precedes effect. The past influences the future. The future cannot influence the past. This is not a constraint that physicists imposed on nature. It is the framework within which the concept of a physical law has any meaning. Without causality, the concept of a physical law dissolves. If an effect can precede its cause, then the relationship between any two events is ambiguous. If the future can influence the past, then the notion of explanation, of why something happened, becomes undefined. Causality is not just a law of physics. It is the precondition for physics to exist as a discipline. Now consider this. In 1949, the mathematician Kurt Gödel, the same Kurt Gödel who proved the incompleteness theorems that shook the foundations of mathematics, presented Albert Einstein with a solution to Einstein's own field equations. Gödel's solution described a rotating universe, a universe in which matter rotates on a cosmic scale, mathematically valid, consistent with all the requirements of general relativity, a legitimate solution to the equations that Einstein had spent a decade deriving. In Gödel's rotating universe, closed timelike curves exist everywhere. A closed timelike curve is a path through spacetime that returns to its starting point in both space and time. An observer following such a path would travel forward in time, always forward, always obeying the local laws of physics, and arrive at a moment in their own past. The curve is closed. The return is to where and when they began. Gödel presented this solution to Einstein as a birthday gift. Einstein was troubled by it for the rest of his life. Not because the mathematics was wrong. The mathematics was correct. The solution satisfied the field equations. But the solution permitted time travel to the past, and time travel to the past permits causal paradoxes. Paradoxes in which effects precede causes. Paradoxes in which the most fundamental law of physics is violated. Einstein's equations allowed it. Einstein did not know what to do with that. In this video, we are going to go through what closed timelike curves are, why they appear in the mathematics of general relativity, what physical scenarios produce them, and what the three possible responses to their existence say about the nature of causality and the structure of reality. There is something in the fifth section of this video that most physicists who work on this problem find the most disturbing. Not the grandfather paradox, not the Gödel universe, but a specific result from 1992 that showed CTC regions could in principle be created by human-level technology given sufficient energy, and what that result implies about why we have not observed any travelers from the future. Stay with me. The logic breaks early and breaks often. Before we go further, Kurt Gödel presented Einstein with a solution to Einstein's own equations, showing that time travel to the past is mathematically permitted. Einstein was troubled by this for the rest of his life. Drop a comment. Do you think Einstein's discomfort was scientific or philosophical? And does the distinction matter? To understand closed timelike curves, you first need to understand the concept of a worldline, the path an object traces through spacetime as it moves through time. In ordinary three-dimensional space, the position of an object at any moment is described by three coordinates, x, y, z. In four-dimensional spacetime, the framework of special and general relativity, the position of an object is described by four coordinates, three spatial and one temporal. As time passes, the object traces a path through this four-dimensional space. That path is its worldline. Your worldline began at your birth. It will end at your death. At every moment between these two endpoints, your worldline records where you were in space and when you were there. The worldline is the complete space-time history of an object. The character of a worldline is constrained by physics. In special relativity, no massive object can move faster than light. This constraint means that worldlines of massive objects, called timelike worldlines, must always point in the direction of increasing time. You cannot reverse your direction in time the way you can reverse your direction in space. Your worldline always moves forward. This forward orientation is the local arrow of time. At every point on your worldline, the next point is in your future, later in time, not earlier. The worldline cannot fold back on itself locally. But locally is the key word. In general relativity, spacetime is not flat. The presence of mass and energy curves spacetime. This is the geometric description of gravity. The curvature of spacetime affects the geometry of worldlines. A worldline that always points locally in the direction of increasing time, always respecting the local constraint, can, in a sufficiently curved spacetime, return to its starting point in both space and time. Imagine drawing a line on a flat surface, always pointing in the same local direction. The line goes straight. Now draw the same line on a curved surface, the surface of a sphere, for example. The line curves with the surface. If the surface curves enough, the line can return to where it started. A closed time-like curve is the space-time analog. A worldline that always points locally in the direction of increasing time, always respecting the constraint that massive objects cannot move backward in time locally, but curves through a sufficiently curved spacetime and returns to its starting point in spacetime. An observer following a CTC would not experience anything unusual locally. At every moment, they would be moving forward in time. Their clocks would tick normally. Their physics would work normally. But when they returned to their starting point, when the curve closed, they would find themselves at the same location in both space and time as when they began. They would be in their own past, not approximately, not near their past, exactly at the same space-time event from which they departed. This is what a closed time-like curve means geometrically. The question is whether it can actually occur, whether the curvature of space-time in any physically realizable scenario is sufficient to close a time-like curve. Gödel showed that it can, in a rotating universe. The mathematical definition of a closed time-like curve requires that the curve be both time-like, meaning it represents the worldline of a massive object moving at subluminal speeds at every point, and closed, meaning it returns to its starting space-time event. The existence of CTCs in a space-time is equivalent to the violation of the chronology condition, the requirement that no closed time-like curves exist anywhere in the space-time manifold. The chronology condition is violated in the Gödel spacetime, in certain regions of the Kerr spacetime, rotating black holes, in wormhole spacetimes with appropriately constructed mouths, and in the region beyond the inner horizon of a Reisner-Nordstrom charged black hole. Let's go through the Gödel universe in detail, because it is the simplest and most philosophically direct demonstration that general relativity permits closed time-like curves. In 1949, Kurt Gödel published a paper in Reviews of Modern Physics titled An Example of a New Type of Cosmological Solutions of Einstein's Field Equations of Gravitation. The paper is one of the most unusual in the history of physics, a rigorous mathematical solution to the fundamental equations of general relativity that produces consequences that most physicists of the time were deeply reluctant to accept. Gödel's solution describes a spacetime filled with uniformly distributed, pressureless dust, a simplified model of matter that rotates as a whole. Not individual objects rotating around a center, the entire matter content of the universe rotating, in the sense that each piece of matter has angular momentum relative to the local inertial frames defined by neighboring matter. In this rotating universe, the spacetime geometry has a specific property. For any event, any point in spacetime, there exist closed time-like curves passing through it. Not just in some special region, everywhere. Every event in the Gödel universe lies on a closed time-like curve. An observer in the Gödel universe could, in principle, follow a path through spacetime, always moving forward in local time, always following a physically allowed trajectory, and return to the exact moment and place from which they departed. They could shake hands with themselves from the past. They could observe events that they themselves caused in what they experienced as the future. The Gödel universe is not our universe. Our universe is expanding. The galaxies are receding from each other in all directions. The Gödel universe does not expand. Our universe does not appear to have a global rotation at any detectable level. The Gödel universe requires it. But the Gödel universe is a mathematically valid solution to Einstein's equations. It satisfies every mathematical requirement of general relativity. The equations that describe the most fundamental theory of gravity we have, the theory that correctly predicts the bending of light around massive objects, the existence of gravitational waves, the behavior of binary pulsars, the evolution of the universe on cosmological scales, permit a universe in which time travel to the past is possible for any observer at any location. Einstein read Gödel's paper. He wrote about it in his response to Gödel's contribution to the Schilt volume of the Library of Living Philosophers, published in 1949. Einstein's response was careful. He acknowledged that Gödel had found a valid solution. He noted that the solution raised troubling questions about the nature of time. He expressed hope that a physical argument could be found to exclude such solutions from consideration. He did not find one. He could not find one, because there is no mathematical argument within general relativity that excludes the Gödel solution. It satisfies the equations. The equations allow it. Einstein spent the last 6 years of his life troubled by the implications of a solution to his own theory. The solution is correct. The implications are unresolved. Gödel's 1949 paper was published in Reviews of Modern Physics as part of a special issue honoring Einstein's 70th birthday. The paper is remarkable for its combination of mathematical rigor and philosophical depth. Gödel argued not only that CTCs exist in his solution, but that their existence poses a fundamental problem for the concept of objective time in general relativity, that time, in a universe with CTCs, cannot be meaningfully defined as a global quantity flowing in one direction. This philosophical argument anticipates the modern debate about the block universe and the arrow of time. Gödel went further than just presenting the mathematical solution. He used the Gödel universe to make a philosophical argument about the nature of time. The conventional understanding of time, shared by physicists and non-physicists alike, involves a notion of objective present. There is a now that is the same for all observers. The past is fixed. The future is open. Time flows in one direction. The Gödel universe challenges this at a fundamental level. In a universe with CTCs, the distinction between past, present, and future loses its objective meaning. If you can travel to your own past, then your past and your future are not separated by an absolute boundary. They are connected by a loop. The ordering of events, which came first, is not absolute. It depends on the path you take through space-time. Gödel argued that this showed that time, as ordinarily understood, does not exist in any fundamental physical sense. What we call time is a feature of our local experience, a product of the specific space-time geometry we inhabit, not a fundamental feature of reality. This is a strong philosophical claim. It was not universally accepted then, and is not universally accepted now. But it follows from taking the Gödel solution seriously as a description of a physically possible type of universe. The argument is still cited in philosophical discussions of the nature of time. The physics has moved on, the Gödel universe is not our universe, and other scenarios for CTCs have been identified that are more physically motivated. But the philosophical implications of Gödel's argument remain unresolved. The Gödel universe demonstrates that closed timelike curves are permitted by general relativity in principle, but Gödel's universe is not our universe. The more important question is whether CTCs can exist in solutions to general relativity that describe physically realistic scenarios that could occur, at least in principle, within a universe like ours. The answer is yes. and the most physically significant examples involve rotating black holes and wormholes. The Kerr solution to Einstein's field equations, discovered by New Zealand mathematician Roy Kerr in 1963, describes the spacetime geometry of a rotating black hole. Unlike the Schwarzschild solution, which describes a non-rotating black hole and has a single event horizon and a singularity, the Kerr solution has two event horizons, the outer horizon and the inner horizon, and a ring singularity. The ring singularity, a singularity in the shape of a ring rather than a point, has a remarkable property. In the region near and inside the ring singularity, the Kerr spacetime contains closed timelike curves. An observer who falls into a rotating black hole and survives the passage through both horizons, which requires specific conditions, enters a region where CTCs exist. In principle, such an observer could follow a path through this region that returns them to their own past. The practical barriers are enormous. Crossing the inner horizon of a Kerr black hole may involve encountering the Cauchy horizon, a surface beyond which the classical predictability of general relativity breaks down. Whether the Cauchy horizon can be crossed in a realistic physical scenario, or whether quantum effects, instabilities, or other processes make it impossible, is an open question. A 1991 paper by Eric Poisson and Werner Israel proposed that the inner horizon of a rotating black hole is subject to a mass inflation instability, a rapid growth of curvature near the Cauchy horizon that may destroy any observer attempting to cross it. The strong cosmic censorship conjecture, proposed by Roger Penrose, suggests that the Cauchy horizon is not physically accessible and that the singularities associated with it are always hidden from outside observers. If the strong cosmic censorship conjecture is correct, the CTC region inside a Kerr black hole is not accessible from the exterior. It exists in the mathematics, but cannot be reached by any physical observer. The conjecture has not been proven. It remains one of the major open problems in mathematical general relativity. Wormholes, hypothetical connections between distant regions of spacetime, provide a different route to CTCs. In 1988, Kip Thorne and colleagues showed that a traversable wormhole with appropriately accelerated mouths could create a time machine. The mechanism involves exploiting time dilation. If one mouth of the wormhole is accelerated to relativistic speeds and then returned, it will be younger than the stationary mouth due to time dilation. An observer entering the younger mouth would emerge from the older mouth at an earlier time, earlier relative to the external universe. The CTC region created by such a wormhole time machine is not a pre-existing feature of the spacetime. It is created by the construction and manipulation of the wormhole. This is a fundamentally different scenario from the Gödel universe or the Kerr interior. It is a CTC region that is created by an agent with sufficiently advanced technology. Thorne's 1988 paper was not a proposal for building a time machine. It was an analysis of what general relativity permits and what constraints any time machine must satisfy. The constraints are severe. Traversable wormholes require exotic matter with negative energy density, and the stability of such a wormhole under quantum effects is uncertain. But the analysis showed that general relativity, as a classical theory, does not forbid the creation of CTC regions by technological means. Roy Kerr discovered his solution to Einstein's field equations in 1963, presenting it at a conference where, according to accounts, the announcement was initially met with skepticism. The Kerr solution is now considered one of the most important exact solutions in general relativity, describing all astrophysically relevant rotating black holes. The existence of CTCs in the Kerr interior was identified shortly after the solution was published. The Kerr-Newman solution, 1965, extends the result to charged rotating black holes and also contains CTCs in the interior region. The mass inflation instability of the Cauchy horizon was analyzed by Poisson and Israel in a 1990 Physical Review D paper. Stop here. The Kerr solution, which describes every rotating black hole in the universe, including Sagittarius A star at the center of the Milky Way, contains closed timelike curves in its interior. If the strong cosmic censorship conjecture is false, if the Cauchy horizon can be crossed, then every rotating black hole in the galaxy contains a region where travel to the past is in principle possible. Drop a comment. Do you think the censorship conjecture is true? And does it matter whether it can be proven or only conjectured? Every discussion of closed timelike curves eventually reaches the paradoxes. They are not peripheral concerns, they are the central problem. The most famous is the grandfather paradox. You travel back in time and kill your grandfather before your parent was conceived. You are never born. You never travel back in time. Your grandfather is not killed. You are born. You travel back in time. You kill your grandfather. The loop is logically inconsistent. There is no assignment of truth values to the events that makes all of them simultaneously true. The grandfather paradox is not a technical difficulty. It is a logical contradiction. If CTCs exist and can be traversed, the grandfather paradox, or some version of it, seems to be possible. And a logical contradiction is not a physical prediction. It is a sign that something is wrong with the theory or the scenario. There are three responses in the physics literature. They are mutually exclusive. They have different implications for the structure of reality, and none of them has been definitively established as correct. The first response is chronology protection. Stephen Hawking proposed this in a 1992 Physical Review D paper, the same paper that introduced the chronology protection conjecture for wormhole time machines. Hawking argued that the laws of physics, possibly including quantum effects that go beyond classical general relativity, conspire to prevent the formation of closed timelike curves. The argument is not a mathematical proof. It is an observation that in every known scenario where classical general relativity would permit a CTC region to form, accelerated wormhole mouths, spinning up a Kerr black hole beyond a critical rotation rate, quantum effects appear to intervene. Virtual particles accumulate near the CTC region, producing a divergence in the energy-momentum tensor that would destroy the CTC before it could form. The chronology protection conjecture is supported by calculations in quantum field theory in curved spacetime. It is not proven. There may be CTC scenarios where the quantum back reaction does not prevent the formation. The conjecture is not a theorem. The second response is the Novikov self-consistency principle. Named after the Russian physicist Igor Novikov, this principle states that any events occurring on a closed timelike curve must be globally self-consistent. They cannot create logical contradictions. Under this principle, if you travel to the past, everything you do there is already part of what happened. You cannot kill your grandfather because the causal structure of space-time makes it impossible. Not through any external force, through the logical requirement that the loop be consistent. The Novikov principle does not prevent time travel. It constrains what can happen during time travel. The grandfather paradox is not resolved by preventing travel to the past. It is resolved by making it impossible for the traveler to actually kill their grandfather. The gun jams, the aim is off. A heart attack occurs at the critical moment. Something always intervenes to maintain consistency. This is a deeply strange picture of reality. The physical world conspires to maintain the consistency of causal loops. Free will, the ability to make choices that genuinely could have been otherwise, becomes problematic. If you cannot kill your grandfather no matter how hard you try, in what sense is your inability a consequence of your own agency rather than the structure of space-time? The third response is the many worlds interpretation. The possibility that time travel to the past creates a branch in the wave function of the universe. You travel back, you kill your grandfather, and the result is not a paradox, but a new branch of reality in which you were never born. The original branch, in which you were born, traveled back and killed your grandfather, no longer has you in it after the travel. You are now in a parallel branch. The many worlds interpretation resolves the grandfather paradox by allowing the contradiction, but placing it in a different branch of the wave function from the one you inhabit. You can kill your grandfather, but doing so does not prevent your birth. It creates a new branch in which you were never born, while the original branch continues without you. The many worlds resolution of the grandfather paradox is internally consistent. It requires accepting the many worlds interpretation of quantum mechanics, which is a legitimate position in the foundations of quantum mechanics, though not universally accepted, and extending it to cover time travel scenarios. 3 resolutions, none proven, none ruled out. The paradoxes remain open. Hawking's 1992 Physical Review D paper, Chronology Protection Conjecture, analyzed the behavior of quantum fields near forming CTC regions and argued that the energy-momentum tensor of quantum vacuum fluctuations diverges as the CTC region forms, providing a physical mechanism that prevents its formation. Hawking noted the result was consistent with CREMA, but did not prove CREMA, the chronology protection conjecture. He quipped that the conjecture was supported by the fact that we have not been invaded by hordes of tourists from the future. Subsequent work has found both supporting and complicating evidence for the conjecture in different CTC scenarios. Let's go through the Thorne wormhole time machine in detail, because it is the most physically concrete CTC scenario and the one that produces the most specific and most alarming implications. Start with a traversable wormhole, a hypothetical tunnel connecting 2 distant points in spacetime with mouths large enough for a human being to pass through without being destroyed by tidal forces. We discussed traversable wormholes in an earlier video. They require exotic matter with negative energy density to keep them open, matter that has not been confirmed to exist in the required quantities, though the Casimir effect provides a laboratory demonstration of negative energy density on small scales. Assume, for the sake of the analysis, that you have such a wormhole. You have 2 mouths, mouth A and mouth B, connected by a traversable tunnel. Entering either mouth brings you immediately to the other mouth, regardless of the external distance between them. Now take mouth B and accelerate it to a relativistic speed, a significant fraction of the speed of light, using some propulsion system. Maintain this acceleration for a period of time, and then bring mouth B back to its starting position. Due to special relativistic time dilation, mouth B has aged less than mouth A during the acceleration. If mouth B was accelerated for what mouth A experiences as 10 years, and if the acceleration was sufficient, mouth B may have aged only 1 year during that period. Now the 2 mouths are in the same location, or close to each other, but they are at different times. Mouth A is in the year 2040. Mouth B is in the year 2031. An observer who enters mouth A in the year 2040 and exits mouth B arrives in the year 2031. They have traveled back 9 years in external time. If they then wait 9 years in the external universe, watching the years pass from 2031 to 2040, and then enter mouth B in the year 2040, they can exit mouth A and find themselves in the year 2031 again, a closed timelike curve. The Thorne time machine is not a machine in the sense of a device you build from scratch. It is a consequence of having a traversable wormhole and being able to accelerate one mouth to relativistic speeds. The construction requirement is the wormhole, the most exotic requirement. Everything else follows from known physics. Thorne's 1988 paper noted a specific disturbing feature of this scenario. The CTC region created by the wormhole time machine is not pre-existing. It is created at a specific moment in time, the moment when the temporal separation between the 2 mouths first equals the transit time through the wormhole. Before this moment, the wormhole is a spatial shortcut, but not a time machine. Entering mouth A brings you to mouth B at the same external time. After this moment, the CTC region exists. Entering mouth A in the year 2040 brings you to mouth B in 2031. The creation of the CTC region is an event with a specific spatial and temporal location, and Hawking's chronology protection conjecture, applied to this scenario, predicts that quantum effects will destroy the wormhole at precisely this moment, before the CTC region can form. If chronology protection is correct, every attempt to create a time machine using a wormhole will result in the wormhole being destroyed at the moment of its first use as a time machine, not by any external force, by the accumulation of quantum vacuum fluctuations at the forming Cauchy horizon, the boundary of the CTC region, which produce a divergence in energy density that tears the wormhole apart. The time machine destroys itself the moment it is first turned on. This is not proven. It is the chronology protection conjecture applied to a specific scenario, but the calculation is consistent with every scenario that has been analyzed. No counterexample, no scenario where a CTC forms without a divergent quantum back reaction has been found. The universe, if Hawking is right, actively prevents the formation of CTC regions, not through any philosophical preference for causality, through a physical mechanism, quantum vacuum fluctuations, that makes CTC formation dynamically impossible. If Hawking is wrong, then time machines are physically possible, and the absence of tourists from the future requires a different explanation. The Thorne, Morris, and Yurtsever 1988 Physical Review Letters paper, Wormholes, Time Machines, and the Weak Energy Condition, was the first systematic analysis of how a traversable wormhole could be converted into a time machine through relativistic acceleration of one mouth. The paper was written in response to a request from Carl Sagan, who was writing the novel Contact and wanted to know if wormhole travel was consistent with known physics. The paper's analysis of the energy conditions required for traversable wormholes, specifically the violation of the weak energy condition requiring exotic matter with negative energy density, remains the foundational reference for wormhole physics. The question of whether closed timelike curves are physically possible ultimately requires a theory of quantum gravity, a complete theory that correctly describes the behavior of spacetime at the quantum level. Classical general relativity, the framework in which CTCs are permitted, does not include quantum mechanics. The chronology protection conjecture is based on calculations in quantum field theory in curved spacetime, a hybrid framework in which quantum fields propagate on a fixed classical spacetime background. This framework is an approximation. It breaks down in precisely the regimes that are most relevant to CTC formation, near Cauchy horizons, near Planck scale energies. A complete theory of quantum gravity would determine, definitively, whether CTCs are possible. If the theory forbids them through some fundamental mechanism, if the chronology protection conjecture can be derived from the axioms of quantum gravity rather than merely supported by sinomial calculations, then CTCs are truly impossible and the question is closed. If the theory permits them, if there exist quantum gravitational states that include CTC regions, then the question becomes more complex. What are the rules for consistency? Which of the three paradox resolutions is correct? What physical observables distinguish a spacetime with CTCs from one without? We do not have a complete theory of quantum gravity. String theory and loop quantum gravity are the two leading approaches, and neither has produced a definitive result on the question of CTC permissibility. What we do have are insights from the ADS/CFT correspondence, the duality between a theory of gravity in anti-de Sitter space and a quantum field theory on the boundary of that space that suggests certain features of quantum gravity. In the ADS/CFT framework, the boundary quantum field theory is unitary, it conserves information, it evolves deterministically. Unitarity is difficult to reconcile with the existence of CTCs in the bulk gravitational theory, because CTCs introduce a kind of causal ambiguity that is hard to map onto a unitary boundary theory. This has led some physicists to argue that the ADS/CFT correspondence implicitly supports chronology protection, that a consistent quantum gravity theory must forbid CTCs. But this argument is indirect and not universally accepted. The honest state of the question is this: classical general relativity permits CTCs. Semi-classical calculations suggest that quantum effects prevent their formation. A complete theory of quantum gravity does not yet exist to settle the question definitively. We know that the equations permit time loops. We do not know whether the universe does. The relationship between the ADS/CFT correspondence and chronology protection was analyzed by Maloney, Song, and Strominger in a 2009 Journal of High Energy Physics paper. They found that the partition function of the boundary CFT in certain geometries is inconsistent with the existence of CTCs in the bulk geometry, suggesting that the boundary unitarity requirements may implicitly forbid CTC spacetimes. This result is one of the most concrete connections between quantum gravity and the chronology protection conjecture, though it applies only in the specific ADS/CFT context and not to general spacetimes. Causality is the most fundamental law in physics. Einstein's field equations permit solutions in which it is violated. The Gödel universe, a rotating universe in which every observer can travel to their own past, satisfies the equations of general relativity in every detail. The Kerr solution, which describes every rotating black hole in the universe, contains a CTC region in its interior. The Thorne wormhole time machine, a traversable wormhole with an accelerated mouth, creates a CTC region through known physical mechanisms. 3 scenarios, 3 different physical implementations, all permitted by classical general relativity, all producing the same consequence: paths through spacetime that return to their starting point in time as well as space. The grandfather paradox arises in all 3. 3 resolutions have been proposed: chronology protection, Novikov self-consistency, many worlds branching. None has been proven. None has been ruled out. The resolution that most physicists currently favor is chronology protection, the conjecture that quantum effects prevent CTC formation in every physically realistic scenario. This conjecture is supported by sequelized calculations. It is not proven. It cannot be proven without a complete theory of quantum gravity that we do not yet have. Einstein spent the last 6 years of his life troubled by Gödel's solution. He looked for a physical argument to exclude it and could not find one. The equations he spent a decade deriving, the equations that describe gravity with extraordinary precision across every scale we can measure, permit a universe in which you can shake hands with yourself from the past. He presented no resolution. He expressed hope that one could be found. 75 years later, the hope is still outstanding. The equations still permit it. The physical argument for exclusion is still a conjecture. The question of whether the universe allows loops in time remains, as of current physics, unanswered. One question: if the chronology protection conjecture is false, if CTC regions can form and be traversed, and you had access to a Thorne wormhole time machine, what is the first thing you would do with it? Not the most useful, not the most ethical, the first thing, the instinctive thing. Drop your honest answer below. I want to know what people actually reach for when they imagine the impossible becoming possible. Next video: why the speed of light is what it is, and what would happen to the universe if it were different. Not slightly different, fundamentally different. What physics, chemistry, and biology look like when you change the one constant that sets the scale of all electromagnetic interactions. See you there.